Hello and welcome to the first session of the day. My name is Brian Tipper. I'm the VP of Sales and Marketing here at OptiWave, and I'll be assisting your host, Ahmed Attia. This webinar will be the second segment of our advanced applications for our OptiSystem software tool, and it's going to be the final segment of the series for OptiSystem. As with previous sessions, we will launch 3 polls that we'd appreciate you all to vote on. We'll also have 2 question and answer periods at the halfway mark and at the end of the webinar. And you'll also notice that there is a handout available in the GoToWebinar control panel. Feel free to download this at any time. And finally, we'll be recording this webinar and emailing the link to everybody tomorrow at 10 a.m. Eastern Standard Time. With that said, let's get the webinar underway. I'd like to introduce your host, our Director of Optical Systems, Ahmed Attia.
Okay, good morning, everyone. Today's webinar would be about advanced applications. And the main application here we're going to talk about it is about Raman amplification. So the webinar will, in the webinar, we're going to talk about some basics about Raman nonlinear effect, and then we go into the OptiSystem Raman amplification capabilities. We're going to talk about the models used in the OptiSystem software. Then we're going to talk about component description and setting. And then we're going to take a few examples about using Raman amplification. Then we hopefully get some questions and answer them at the end of the presentation. So as we know, optical fiber suffer from different impairments, and these impairments include nonlinearity, dispersion, attenuation. And in this webinar today, we're going to concentrate on nonlinearity part. And as you see in the nonlinearity is coming from the part which is related to refractive index of the optical fiber, which is composed of 2 parts. It's the linear part and a nonlinear part. The linear part basically is frequency dependent and causing dispersion, mainly in single mode fibers. And the nonlinear part, which is basically is composed of 2 terms. One is the N2, which is nonlinear coefficient, and the I, which is intensity. So as you see, the intensity, which is related to the peak power of the pulses or the CW light propagated inside the fiber, and divided by A effective, so which is the effective mode area of the fiber. If you decrease A effective, you increase the intensity, thus you increase the nonlinear refractive index, and thus you have more nonlinear effects in the fiber. The same thing is you can increase your power level, you increase your intensity, and thus also increasing the nonlinear refractive index, and hence you're gonna have more nonlinearity in the fiber. Now, if you propagate light inside the fiber, typically the propagation is governed by nonlinear Schrödinger equation, which is shown here. The main terms in the equation is the attenuation, as we see here, this term, and then the dispersion term, which is related to the group velocity dispersion, and the third order dispersion term. This is the nonlinear term, which is mainly related to the self-phase modulation, nonlinear effect, self-steepening, and then this term, which is related to the stimulated Raman scattering nonlinear effect. And today we're going to talk about mainly about stimulated Raman scattering, nonlinear effect, and Raman amplification. So the physics behind it, it's coming from, if you look at the silica lattice, the glass lattice, you can see that we have this IO2 and a silicon atom and 2 oxygen atoms connected to it. Then this structure, which is the optical fiber cables, when they vibrate, they generate sound waves. When light propagates through the fiber, the light photons is gonna hit the sound waves, and the impact will create photons basically. These photons gonna scatter in both directions in the stimulated Raman scattering effect. When they scatter in both directions, they generate what is called stocks and anti-stocks waves. This in the optical fiber, typically these stocks are about 110 nanometer far away from the bump signal, which is has to have certain amount of power in the fiber. Now, if we launch another signal with the bump, and this signal, if we align it or we tune the bump such that the 110 nanometer is lying down with the signal level, then we should be able to transfer energy from the bump to the signal, and then the Raman amplification effect occurs. In this part here, we're going to talk about basically the capabilities of the OptiSystem in working with Raman amplification, and the tools, the simulation tool, allow us to basically do forward and backward bumping of signals to transfer its energy to the signal, the information carrying signal. And we can use single or multiple lasers in the projects, as well as we can use monodirectional or bidirectional optical fiber. So we can use these types of components in the OptiSystem software. Also, the software it also enables us to optimize the bump's wavelength and power level. So basically, the wavelength important, as I mentioned earlier, we need to tune it to be able to transfer the energy efficiently to the signal. And the power level also, we need to control it in order to make sure that the different WDM signals will somehow get equivalent or not equivalent, or make the spectral amplified signals flat as possible. We're going to get example here about the optimization of the wavelength and power level to get the flat amplified DWDM signals. Then also the software enable us to study and investigate the interaction between the different wavelengths propagating in the optical fiber, and this is especially to study the gain tilt effect in the caused by Raman nonlinear effect. And also the software would enable us as well to enable or conduct transmission experiments using the Raman amplification. In this part, we're going to talk about the models used for the Raman amplifiers. And in these models, basically, we consider many physical effects where we investigate or calculate the bump-to-bump interaction, signal-to-signal interaction, bump-to-signal interaction. As well, we consider the Raman's spontaneous emission and its dependency on temperature. We consider in the models the stimulated Raman scattering, nonlinear effect, which we mentioned it earlier, and also we consider the bump depletion caused by the transfer of energy to the signal, and also we may consider in the simulation tools the relay scattering. Here's basically a reference which can be referred to in terms of more details on the these interaction models. In the OptiSystem, we basically look into two types of models here. One model is called the interband Raman scattering model, and in this model, it's used basically for the signals or optical fields where the polarization is maintained along the fiber length. And in this model, basically, you have to set the mod type or model type into a scalar approach. So this is, I'm going to show it to you later on how to set the model type into scalar approach, and once it's done, you will be able to use the model where the evolution of the electric field sampled signals, the parameterized signals, as well as noise bands will be calculated. The other model considered in OptiSystem is the complete Raman response. And the complete Raman response, basically, when signals coupling occupying different frequency bands are used. In this model, the evolution of parameterized signals and noise bands only calculated, and the process of the calculation is slower compared to the interband Raman scattering. Now, for this model interband Raman scattering, if we choose the another approach is called vector approach, and the vector approach typically is chosen whenever we have polarization states variation of the signals propagating in the fiber. So if the polarization is not preserved of these signals during propagation, we must use the vector approach. And the vector approach, basically, whenever it is enabled, the stimulated Raman scattering nonlinear effect would be discarded. In some situations where, for example, the user chose the scalar approach, however, the user set, for example, the BMD into a stochastic instead of deterministic model, then the Raman amplification model would be automatically use vector approach, as well as the when, for example, the user uses two polarization identified at the input of the fiber, then as well as if the user set up to scalar approach, however, the simulations conducted inside the OptiSystem software will be using vector simulation. In this part here, we're going to start looking into the main components and their parameter setting of Raman amplifier. And the project, which is going to talk about it later on, basically, it's used for broadband amplification. But now, if you look at the main components here, we're going to look into, for example, the sources here. We use CW signals. The signals we use are, for example, you can set the number of channels or ports you need to use. In this example, we use 24 CW channels. The frequency is set at 1620 nanometers. The frequency spacing, so between the wavelengths, is -4 nanometers. And you can set up the power level here. You can set extension ratio and line width of the laser. You can set the bit rate, which is set up globally by the bit rate in the system. So if you look at the global bit rate here, it sits at 2.5 gigabit per second. So going back again here, you can set also the order of the random bit sequence generator. So if you evaluate the script here, we have order 4 is used. Then you can set up the rise time of the pulses. You can set relative intensity noise or disable it. You can set chirp parameter. So many parameters you can set them. You can set the noise bandwidth for this component. Also, the other component we need to use, so we need to multiplex these lasers to be able to launch them into the fiber. So we use another component, which is a multiplexer. In this multiplexer, we use an ideal multiplexer. So you need to set up the same number of channels for the source, and you can set up your own attenuation or losses for the component. Now, the other component is the fiber. So we have two types of fibers. Libraries right now, components we have. One of them is the bidirectional, where the signal can go into the forward direction, and the signal in the backward direction also could be calculated in the simulation tool. In this component, this is the major component you're gonna need to set up in this when you use Raman amplifiers. The first tab here is the main tab, where you define the length of the fiber. Then the attenuation data. So the attenuation data, you might have it as constant, or you might have it as from a file. So you read it from a file. Then the other parameter, if you set this as from file, you enter the file path here. Then you need to set up the effective area type, either from two options. You can have constant option, where if you choose constant, it means all the wavelengths have the same value. If you use it from file, so you can have its wavelength dependence effective area. In this situation, if you choose a constant, you're gonna use 72 micrometer square for the effective mode area. The other parameter here is the Raman gain type. So you can have different options here. You can have Raman gain efficiency or Raman gain type, and then you can set up the peak Raman gain value, and you can set up here the Raman gain reference pump. So this is the wavelength, which is you set up your reference wavelength, and the Raman gain will be defined based on this wavelength. And then gain profile, you can get it from, if you choose, for example, from file, you can get the Raman file from here. The other parameter here in the enhanced, you can see you can set up the temperature. As we said earlier, we can study the temperature dependence of the interaction. You can set a parameter here, polarization effect, which depends on the polarization between the signal and the pump. You can enable relay backscattering parameters, dispersion parameter, and you can enable it or disable it. In the numerical part, you can adjust the number of divisions in the calculation, number of iterations in the calculation. You can look into the simulation here. In terms of noise, you can set up the center frequency, the noise bandwidth, and everything else. The other parameter here is on the other side, which is the bump side, because we have backward bumping in this scenario. So the bumps are defined here, where we have, for example, number of output ports is 12. You have line width 100 megahertz. And then if you look at the frequency, you define the wavelength here. So again, the wavelength is very important to enable the proper control of the flatness of the amplified signal in DWDM system. So you have to choose properly the wavelength to be able to get efficient control of the flatness. Here you can control also the power levels. It's not necessarily to have the same power level for every bump, and that's because of the non-flatness Raman gain profile. You can control the polarization and noise in the system. Here, this is a mux, which is basically you use it to mux the bumps, and this is number of ports, the bandwidth, and number of channels. You have to define them. You can define ripples and noise and everything else. Now, this is the main components in the system. The second part of the components are the visualizer. So you can put, for example, here a spectrum analyzer. Here we have a component which is called the dual WDM analyzer. And now the WDM analyzer has many parameters which can display. It's a very good component, can be used in WDM analysis, where you have many parameters can be measured, calculated, like signal power, noise power, signal to noise ratio, gain. You can calculate noise figure. Many parameters you can calculate using this component. You can have the definition here and frequency in hertz or terahertz, or we can have nanometers. You can have the power in dBm or milliwatt. You can have some kind of detailed analysis here if you press on the second tab, where you can have, for example, minimum values, maximum value of every parameter in the component. Okay, with these components, basically, we can say that this is most components used in Raman amplification. At this moment, I'm going to take a break and allow my colleague to run the second poll, and we continue after that. Thanks very much for listening.
Thanks, Ahmed. The second poll is launched for everybody. Please take a second to answer it. And if you have any questions, please type them into the questions panel. Again, I do see some hands up. We're not taking any questions via the GoToWebinar raised hand option. So please just go ahead and type the questions in, and we'll go ahead and answer as many as we can. Just going to give it another 10 or 15 seconds. And there's some people that have some questions that they'd like to ask. And just to summarize, this is the final OptiSystem session. So thanks to everybody that's shown up to all of them. I know there's a good chunk of people on this list that I'm looking at that have shown up to all 5 sessions or 4 sessions. So thanks for that, and let us know your feedback on this webinar week in general. We'd like to know if this is something useful for you guys to get to use the software, or if we do something in the future, any any advice on how to structure it a little differently that's a little bit more applicable to what you'd like to see in this type of format. Okay, I'm going to go ahead and close the poll, pass it back to Ahmed.
Okay, thanks, Brian, and hello everyone again. So again, continuing now from this part, which we talked about the main components and the settings of them. As again, here we describe the dual port WDM analyzer, what's functionality of it. Now we're going to start with the examples. We're going to talk about 3 examples in this webinar. The first one is how to optimize the bumps, power, and wavelength to enable flat gain amplification of a DWDM system. And then we're going to talk about a broadband backward bumping example where we have signals in the C band and L band, and we allow bump amplification there. And then the last example, we're going to talk about Raman gain tilt investigation, where shows you how the OptiSystem Raman amplification model can investigate this effect when you have different DWDM signals propagating inside the fiber. So the first example here is the example which we discussed a minute ago about launching 4 bumps at different wavelengths in the 14x nanometer range with different power levels, and launch these bumps are used to amplify 64. In this example, we're going to amplify 64 continuous wave channels in the range between 1512 nanometer to 1562.4 nanometers. The wavelength spacing between the channels is 0.8 nanometers. The power level per channel is -17.4 dBm, and the length of the fiber, the bidirectional fiber here, is 25 kilometers. It's a single mode fiber, and this example basically it's one of the examples which you may find in the library of the OptiSystem examples. Now, once you run this example, you can see here basically the amplified signal and the flatness of the WDM signals. If you look at the parameter here, the flatness, the difference between the peaks of these wavelengths, different wavelengths, it's about within 1.5 dB. And typically, like in the industry, the specification in that range or around ±1 dB is some specification set by system manufacturers. This example, if you can see it here in this example, where we run this example, which is here, the optimization of pump. If you look at the parameters used in the example, you can have, for example, attenuation 0.2 dB, which is we use it constant. The effective area is constant, it's just 55 micrometer square, and the Raman gain type is Raman gain here. The relay scattering is constant. The simulation, if you look at the simulation, and then random numbers here, noise, and then if you run this code, it's going to run very fast and do the calculations. And here you can look at the basically the different channels and using the dual port. Oh, what's happened? It's look like the path. Okay, so anyway, so we can look into the second example here, which is if the example it's anyway it's in the system examples, it could be the path is not properly calculated. The output supposed to be in like the gain flatness is 1.5 dB, If you look at the second example is using for broadband backward bumping, which is in this example we're supposed to have this is the lasers. So we have 24 channels, 4 nanometers separation, power level is -5 dBm, and you have the length of the fiber here is 25 kilometers. The attenuation is it's from file. It's loaded from file, and okay, and then the effective area. It's from file as well. You can read it from here. The Riemann gain is from is reading from values. It's here peak value is around 10 minus 1500. The noise, the randomness, and all these parameters are set properly. If you run it, I hope the path is correct. I didn't check it. Okay. So if you look at the parameters, here you go. So if you look at the analysis, you can see here each channel and frequency, the gain of this channel, the input power, how much it is, around -7 dBm, the noise level, the output signal power levels. And if you look at the spectrum analyzer at the input here, you can see this is the channels launched into the fiber, and the output channels, which is launched here. You can see the amplified signals, and this is the noise levels. So all the analysis you can be, again, this example is done in the examples library of the optical amplifiers in OptiSystem. The third example we're going to consider here is the Riemann gain tilt, which is basically we have DWDM channels here. So the example, I'm going to look at it in a minute. So if you go to this example, so in the sources here we have 80 channels going in the C band and L band. These channels have power level of -17 dBm. The channels are launched in the forward direction, the C band, and in the backward direction, which is the L band wavelengths, also with the same power levels. So we have channels, 80 channels going this direction, and they are interacting inside the optical fiber. The optical fiber is a bidirectional fiber. The parameters in it, you have length is 100 kilometers here. The reference wavelength is 150 nanometers. Dispersion is 0.2. Attenuation is 0.2 dB per kilometer. Dispersion is set up to 16.7 picosecond per kilometer nanometer. The group loss dispersion, we selected it, allow it. The BMD is deterministic. The nonlinear models, we allow self-phase modulation, cross-phase modulation to occur. The effective area is constant. The nonlinear refractive coefficient is 26 10 minus 21 meters square per watt. The Riemann gain is calculate. If you go to numerical here, the model type is scalar. So again, you can choose scalar or vector. Depends on the polarization of the signals, if they are preserved or not preserved. If this polarization is not preserved, automatically, even if you select scalar, you're gonna get vector analysis approach. BMD here is deterministic, which means if you put scalar, it's gonna stay scalar. Then relay scattering is not selected, for example, in this example. If you run the example, basically, you're gonna see you're gonna see the different channels here. We compared, and actually we did two examples in the simulation. One example, we used only single fiber, monomode fiber, which is monodirectional fiber, which is the CWDM fiber component. And then we used the bidirectional component, and then we looked at the spectrum of the using SOA, the different channels in the L band and the C band, and we looked at how these channels will interact, as you see again inside the optical fiber, and the interaction is happening because of the Raman nonlinear effect. So you have the C band propagating here, L band is propagating in the backward direction. They are interacting inside, so you have signal-to-signal interaction, and the result will have gain tilt effect. Initially, we have flat gain, and then because of Raman nonlinear effect, you have the tilt is basically the gain is not flat anymore; it's tilted. Now the project here takes a few minutes to run. So in this time, I'm gonna go to the third ball, ask my colleague to run it, and then we can show hopefully the results by the time end of this ball. Thanks very much for listening.
Okay, so I'm going to go ahead and launch third poll for you guys. And there are quite a few questions that came in. I'll let Ahmed decide when he wants to answer those, if he wants to do the results of the last simulation first. But this is the chance to type your questions into Ahmed. You have basically a one-on-one with him right now to ask anything you'd like. And so it's a great opportunity to make use of that. And again, thanks to everybody for joining in on this final OptiSystem session. I'm going to go ahead and close the poll now, pass the mic back to Ahmed to finish up. Ahmed, are you there? I'm not sure if you're speaking with your mic on mute.
Yes, hi. No, I didn't actually listen to that. Your poll is done. Sorry. Okay, so I'm gonna go through I looked at the simulation is still running, so because it's a large number of channels here, it's about maybe a few minutes to finish it. So I'm gonna go to the questions at this moment. So there's a few questions here. One of them says, what is the value of the bump laser used in this example? The bumps, usually in this example is the interaction between the CWDM channels and WDM channels is the issue. So there is no bumps, as you see here in this example, used. So we have CWDM channel, L-band channels here is coming amplified, and then here is C-band channels are amplified and launched into the fiber. So the interaction is occurring because of the signal-to-signal interaction and causing the gain tilt. So there is no bump in here in this example. The other question we have here is the Raman amplifier effect the same in G657 fiber as in G652? So basically, each type of fiber has its own parameters. For us, is important is the mode field effective area is the crucial parameter. So different types of fibers have different effective mode area, and then the nonlinearity interaction would be different. So each type you have to make sure that you use the right parameters of it to be able to get the right simulations. Another question is, are we giving the sample file of the OptiSystem later? So the samples themselves are available in the examples library, as I mentioned in the first webinar. This example, the Raman gain tilt examples, it's not in this example set. However, we will add it up in the next release. But if someone needs it, he can email me directly, and we can pass it to him. Another question is CWDM, DWM signal wavelength should be under 110 nanometer of 980 nanometer Raman bump. Now 980 nanometer is far away from the signals, which is in the C band or L band. Typically in C band and L band amplification, we use 14XX, we call it 14XX, which is like 14 nanometers, like 1450, 400. So if you have 1450 nanometers, typically you amplify signals around 1555, 1560. This is the maximum peak gain you can get from Raman. So this is something which you can use the OptiSystem software to tune the wavelength and get the maximum amplification and lower power for the bumps, because this is an issue of cost, how much bump power you're going to use in the design in your system. The more power, it means more money you're going to pay for the laser. So it's a good tool here for the OptiWave OptiSystem software to use for these kinds of designs. I think I addressed most of the questions. There is a couple of questions. I'm gonna send the emails directly to people who asked them. The thing is, because they are asking different questions, is related to the fiber mode, the polarization mode dispersion designs, so models. So this is we can hopefully send them directly to the question, to the person who asked the question. I had a new question here. Also, this question, I guess, is what we're going to do. We're going to answer it to the person directly, because it's not related to the presentation here. Okay. So with this, I'm going to conclude the webinar. I thank you very much for listening and for attending all these webinars we had this week. Thanks very much. Bye-bye now.